Thank you very much, Verena. So yes, I am Giovanni Rimassa from Martel Innovate, and I am coordinating Hub for Cloud, which is one of the two coordination actions that are part of the Horizon Cloud program. But that's not, in this case, the stage is not for the coordination work, but it is to be given exactly directly to our associated present the results and the discussion about what are the perspectives, let's say, of the work that they have been doing. So you can see already the contributors that will be taking turns into taking us on a journey for these 2 hours about the various aspects of the morphemic and melodic projects. And just to give you a highlight of the agenda, we have basically 4 sections of half an hour each. About in the scene, an introduction of the ideas about multi-cloud and the latest research result and topic. And then we will go on with more practical sections about the deployment and the use cases, and we will finish with a summary about the current research challenges. So I just jumped straight into the first section that is about introducing multi-cloud ideas and the research status at the moment, and we'll give also an overview of the projects Melodic and Morphemic. And the speakers are Geir Hoor from University of Oslo and Maria Di Girolamo from Engineering Informatica SPA. I suppose, Geir, you are first, right? So I will just stop sharing my screen and give you the floor. Thank you very much.
Thank you, Giovanni. May you give me, now I'm had the right, fine, perfect. So I will share. I hope that you see my presentation mode now.
Yeah, all good.
Yes, we see.
Good, so let's go. So good afternoon, everyone, and thank you for this opportunity to present Morphemic and also its predecessor, Melodic, which is a core element of Morphemic as well. And basically, we are talking about autonomic multi-cloud application management. So this is seen from a data center point of view, and we are working on managing for the application owning organization, or the application owner, as we just say it for brief. So what kind of applications are we talking about? Well, of course, you don't need an advanced management solution if you have an application which you start in the cloud that runs for 1 hour and then you have the results. Fine, finished, done. But if you have an application which is distributed so that you have many different components in your application, and these components are exchanging information, whether these components are normal software components. I will use the term components for everything, but they can also be like microservices that you have deployed. They can be services that we are using in your application, calling upon. They could be serverless computing, so functions that you are simply invoking. And it could also be any kind of combinations of these that is basically your distributed application. So this is the first thing, that you have all these, the different kinds of components to look after. Then, and a second aspect is that your application must have variable resource demands, because if you have an application that requires 3 virtual machines, well, then you don't have a problem, because then you can allocate those 3 virtual machines and you can go home and sleep peacefully that night as well. But if you have an application where you have users that comes in, where you have data that might change with time, where you have other things that could influence the execution context. So my classical example is, for instance, if you run an airline scheduling service and suddenly there is snow on an airport, so big airport, say Frankfurt, is closed, then what do you do about all the passengers, all the crews, all the planes that are displaced in wrong locations? You have to reschedule all of this in a very short time, and then when you have done that rescheduling, then your load goes down to normal again. So this is typically a reaction to application execution context. It could also be like Telegram some years back. They crashed deeply because they got a lot of new users in a very short moment, and that was in nighttime in the US. And the result of that was that nobody looked after the servers, and when they crashed seriously. So they were down for about 1 day or 2. So when you do these deployments, you have to find this cost, performance, and of course user experience and your own experience with the application. The applications have to be long running because otherwise you don't need to manage them, and they suffer, as I said, from data dependencies and also from the number of users and how the users are using the application at that particular time. And in general, when we do this kind of management in the cloud, we cannot assume that we know anything about the application. So the application is a black box, and we should not assume that the application owner has to do any kind of change to the application code or application layout or communication in order to use such a management service. So what we are left with is actually only architectural knowledge about the application and how the components are connected together, what they are, and their multiplicity. So what is then the purpose of multi-cloud? Well, my claim is that all applications will, at one point, at least if they have these characteristics on the previous slide, have to go multi-cloud by one way or the other, because if you have a permanent load that you need to satisfy, so if you do this airline scheduling, then you will probably do this every night for your fleet of airlines and a fleet of passengers and fleet of crew and set of crews, and this will happen every night. So this is something that you know in advance, and you'll probably not use cloud for that, because that what you will do is that you will use a permanent infrastructure, your own private infrastructure for these permanent calculations. And when you have these exceptional situations like snow on the airport, then you will scale out and use rented resources to cover these additional peak requirements that you have. In addition, now these days, there's more and more work and computations that can be done. Excuse me, sorry about that. We talk about, for instance, GPUs, so graphical processing units. We talk about tensor processing units, and we talk about ASICs, FPGAs, dedicated hardware, which is able to run parts of the application in a much faster way. For instance, encryption can be done extremely fast on FPGAs. However, once you have done the encryption, then if there is 3 hours until next time you need to do the encryption, then you will have the FPGA idling. So renting the FPGA for this kind of limited time acceleration could be beneficial for you. And this means that you have to, again, be able to use the resources for a limited amount of time and then go back to your standard permanent load. And then you have the cloud continuum. So the cloud is no longer just about data centers. The cloud is about everything which goes from the data centers, but also all up to the users and the users' mobile devices even. So you have to cover the full range of everything which is between the data centers and your users' applications and users' applications in your deployment. And finally, then by having the possibility to go multi-cloud, then you avoid having a lock-in with one vendor. So for instance, we had an issue last year where a data center in France burned. And this is, of course, an extreme situation. But if you then had only that data center provider as your cloud provider, then you might run into a disruption of your application because they need to restart your application on the resources they have available at the moment. And of course, even Amazon, the biggest cloud provider in the world, will have outages, will have problems with networks. So there is a good reason, at least only for security, to be able to use more than one cloud provider. Always at the same time, because if you then have an outage with one cloud provider, your machines in other cloud providers are already there, deployed and ready to take over the load from the failing cloud provider. And finally, there could be legal constraints, like, for instance, in Europe, we have GDPR, which means that data related to personal and individual citizens can only be It means that you care about where you store the data, and that the operator at the data center is not under some kind of secondary laws like American operators that will have to open the data for other governments if the other government is, or their home government requires to do so. So all of this is speaking for multi-cloud. And once you have multi-cloud, and once you have this continuum from the cloud to the edge, then of course you have an issue with what is called orchestration, which means that what you need to find a way to deal with all these computing systems and all the software which is involved, not only your own software, but also the operating systems of the different platforms. And as we will come back to, also the networking issues and all that goes along with that. So the only way to do this in orchestration is to achieve automation. So automation means that you are able to do this in an automated way. And we are coming back to that as well, because this is part of the complicating factor. But unless you have some management solution like we are proposing in place, you will have to do this yourself. And that is very, very labor intensive and labor consuming, especially if nothing happens, because then you have to spend employees' time on just and for something for them to do, but you cannot take them away, because then if something happens when they are taken away, then you will have a problem. So basically, you can look at this as repeatedly or iteratively two phases. First, you have to acquire the necessary resources to run the application, and then you have to use these resources in an optimized way. And this is what is called orchestration in the scientific literature, and which is what we are using melodic and morphemic. So the only way to manage such a complex nature is to achieve some kind of autonomicity or autonomic systems that will improve themselves, that will seek a better way and will automatically optimize their operation. And this is sort of the vision of autonomic computing that is now almost 2 decades old. And for those wondering what this picture shows, this picture is an interpretation of the internet and the internet connections between autonomous systems. So this basically shows the very complex topology of the internet today. And of course, the internet is based on these principles where you have these autonomous systems that are managing themselves. So there's nobody designing the overall internet. The internet is just growing where the need is and connected as need be. So from this perspective, the internet is a good picture of what autonomic systems really are. However, in order to make these decisions, we need to figure out what we can do with respect to the user's need, and we need to have a way to represent what the user needs are. And this is what we call utility, and utility is a concept which is behind every choice. So I will always choose, if I'm a rational agent, if I'm a rational person, I will choose the option that gives me the highest utility. So if I go for a red car or a green car, there must be something about those colors that gives me a higher utility for the color I'm selecting, for instance. It's also multidimensional because I'm not only looking at the color of the car, I'm also looking at the engine capacity, the engine size, I'm looking at the consumption, I'm looking at the number of seats because I have to carry the family, etc. So all of this has a multidimensional weight in the decision I'm making based on the utility. The first real good book on this came already in 1970, which is a summary about the economic field's knowledge on utility and how to optimize for utility. We use utility in melodic and morphemic to sort of encode, so we can, in an automatic way, find out what the administrators want. I would like this to be managed from their own view, or how they would like to do it themselves, if possible. So all of this ties in with the autonomic computing vision, and also within that vision, utility plays a key role and has always been a part of the autonomic computing vision. So going autonomic computing also means going for the utility view. I know that utility view might be contested, but I think still it's the only way to achieve some kind of flexibility in the management and achieve the good trade-offs between the different parts we are looking at here. So we start with a model, and this is the so-called made-K loop from autonomic computing. And in this model, we are describing the application, we are describing the goals, and we are describing what kind of measurements will we need to take in order to assess if we are on the right track, if we have the right utility for the owner of the application. Then we have to do this optimization. So we have to look at this utility, and then based on the constraints, for instance, the budget or other constraints like GDPR, then we can do the optimal decisions about this application for the given context. So when the context changes, for instance, the number of users, when the number of users changes, we have a different solution based on the user utility. Then once we have a plan for what is the best configuration of the application under these conditions in this context, then we have to find out how can we go from the currently running application to this new better application, and what are the steps we need to take in order to do that reconfiguration. And the scheduling of reconfiguration actions. And finally, once we have the application deployed, running, and well started, then we have to monitor the application in order to see, are we still on track? Are we within the bounds? Are we within the constraints that have been set by the users for what is assumed a good operation of this application? And if not, then we have to go back and do a new plan and a new analysis of the situation, and then carry on. So this is sort of an infinite loop that we are starting by the first deployment, and then we keep it running. So it means that we need to find a model of the application first, and there are different viewpoints that feed into this model. So for instance, the application developers can inform us about the set of application components and how they are connected and what kind of data sets they're using and what kind of metric values we can measure from these components. So for instance, number of users, this cannot be measured from the cloud deployment platform, but the number of users can be measured from the application itself, because the application knows how many users there are. So this is typically an application level metric. Then we have data managers that are in charge of the data sets and the data bindings for the application, what kind of data is used in computation. And computation is always data transformation. So we have data that calculates something and output coming out of that component. That is all computing is about, fundamentally. So this means that without data, there will be no computation. So data is an important part of this. And then, of course, you have the business view, where you have the utility for the business, and typically how do the business operating this application make money out of this deployment. What is seen from the business point of view, for instance, budget. And finally, you have the system administrator, who is in charge of finding the good cloud providers, the good virtual machines to use for the deployment, and also what kind of constraints do we have on different machines. So for instance, with respect to memory, with respect to number of cores and these kind of things. So what we do is that we encode most of this in a language and domain-specific modeling language called Camel, and it covers the two parts that are in yellow boxes here. And based on the information given by the user in those yellow boxes, we form a constrained programming model, which we are optimizing runtime in Melodic. So Melodic is basically taking this model as an input, as a first level input, and it's modeled at runtime, so it will be automatically updated whenever Melodic makes a scaling. Then after we have the model, then we optimize and find the best deployment for this particular model under a given context. And of course, in the beginning, we don't have a context, so the optimization will be more or less random in that sense, but within the constraints of the model. We do the deployment, and then once we have the deployment, we install monitoring the application. And these monitors and the monitoring data allows us to build what we can call a context awareness. So we understand what are the current situation for this application, and we evaluate this running situation against the constraints of the model, which means that we are able to reconfigure if the context is out of bound. In other words, if it violates some of the service level objectives of the application. And in that case, we have to go back again to the model, which now reflects the running model. And we have to see what can we do, how can we optimize the deployment so that we are now within the constraints of the model that is in effect. And this goes on and on and on. But there are two observations to be made here. One is that this is a reactive loop. So we have to have the change in the context before we are able to redo the optimization. The other thing we see here is that we are sort of bound to one particular Camel model, and this is sort of what happens at runtime. So once we have this model, we are sort of deploying it and managing that particular model. But if we see other opportunities that could make a better model, it's not possible in Melodic to the model. So what we did when it comes to Morphemic is that we have the application source, and this time we assume that you have a little better view of the application source, and from this you derive this application architecture model similar to what we have in Melodic. But we also realize that there is a lot of open source and the idea is that we can gather this code, we can make a fingerprint of our application and compare it with applications from the open source world. And based on that, we can improve the deployment model by including information about similar applications we have found in the internet. Then we could also take care of the monitored data and store it so that we could use historical time evolution, so that, for instance, we can detect that in the daytime there are many users and in nighttime there are few users, and scale the application according to these kind of variations, which means that we need to have a way to predict the context of the application and how this will evolve over time, so that we are able to put this into the model in terms of constraints, in terms of new kind of components or multiplicity. For instance, instead of saying that the multiplicity of a component is from 1 to 10, we can say that the multiplicity is from 5 to 10, because we know that it will never be useful with less than 5 components or copies of that particular component. And then, of course, the application source can also be compiled in different versions. So, for instance, I said that if I have in my source a part for encryption, then there might be a bit stream for that, so that I can run it directly on an FPGA. So I can choose between running it on versions of the same component, encryption component. And these two versions, which one should I choose? This is an optimization problem. This is an optimization problem of cost. This is an optimization problem of computation time. So then this optimization can again feed back to the architecture model, saying that, okay, don't deploy this, or normally don't deploy this as an FPGA, deploy it as a CPU. But if you detect a bottleneck, and we have a way to discover new capabilities coming from cloud. So if another cloud provider also offers FPGAs, then we need to take that into consideration at the runtime and use this in the optimization problem. But it should be noted that we are not doing anything about the Melodic runtime optimization cycle. but we are changing the Camel model. So all of these observations, all of these intelligence that we are building is like a pre-processor for melodic, for Camel, and aiming at building a better Camel model. So now Maria will talk about what we are doing in order to gather or crawl the open source repositories, and so that we can make a good application profiling. So with this, I pass on to Maria.
Okay, thank you. So. Can you see my presentation?
Yeah,
Yes.
it's in full screen mode.
Okay, good afternoon. My name is Maria Di Girolamo from I'm the intern of the Morphemic Crawler. The presentation is divided into parts. The first part is an overview of the context of which the crawler is implemented, and then I'm going to details the Morphemic Crawler. So the reference context on which the crawler is implemented is the polymorphic adaptation feature. The crawler is the element that drags the web in order to search the information from open source project, gets this information and store it into the specific data warehouse. Next slide, I'll see how. In the morphemic context, this functionality is part of the polymorphic adaptation, and one of the main tasks of the application profiling is one of the tasks of polymorphic adaptation is application profiling. Application profiling is responsible to define the profile of application based on specific characteristics and based on the source code and metadata information in order to define the best deployment model for polymorphic application. In this context, the crawler is implemented. Here we have the architecture that is the results of the implementation and development of the functionality for application profiling. The component is profiler, and the crawler is part of this component. We have other component that is developed and implemented for the other, my colleague. On the Morphemic Crawler. Morphemic Crawler has not been developed starting from scratch, but derives from another European research project called Marcos. Marcos provided a crawler that analyzes software repository mainly to provide the licensing. Morphemic Crawler provided and more oriented to define the profile of application based on the source code, but not only source code, but the other metadata information, as for example, the name of the project, description of the project, license information, the program language on which the application is implemented. Okay, the main functionality of the web crawler so is download the source code and metadata information from specific website. In Morphemic project is called open source project information. They are a set of Forge, MetaForge, and a list of directory from which project metadata is downloaded. And as I said before, here in this picture, we have the list of some of this information, but not also, but the Morphemic Crawler is also responsible to maintain this list of open source projects repository. At the moment in the Homophonic Crawler, we have configured the GitHub, jQuery, and the important role of Homophonic Crawler is to store and maintain this information and to make available to the other Homophonic component, for example, the knowledge base, using the RESTful API. Based on this functionality, the crawling process is implemented. The crawling process is repeated in a loop. The component responsible of the crawling process is orchestrator. The first step of the orchestrator is reading on a configuration file that we have the list of this open source software repository. And after the reading of this configuration file, start the downloading process. For every time that an information is downloaded from this open source software repository, this information is stored into data warehouse in a specific table that Morphemic is called the data fetcher. So for each of these open source software repository, we have a dedicated table. For Apache, we have Apache, the table Apache, and the same for jQuery and GitHub. Another important role of the crawler, before to send the information to the other component of Morphemic, is to collect and reorganize in one only standard JSON format this information. Here we have the model created, provided by the Morphemic crawler and contain all information useful for the other components of Morphemic, as for example, analyzer. Useful information as, for example, as I said before, project name, but not only the name of the project. We have the information useful as, for example, number of the release and the reference link where I can download the specific release. We have other important information, for example, for license or program language. Now we are going to configure other open source software repository. Here we have some example of that. In order to have metadata suitable for polymorphic adaptation, and then I'm going to verify if possible to deploy the crawler in a recent version of the Ubuntu operating system. That's all for me. Thank you.
Thank you very much. I would like to ask if there are already questions from the public in the chat, or otherwise we can proceed with the next section, but we will anyway have a Q&A at the end. But if there is some urgent question, then we can already try to answer it now. So I am sharing my screen again. Sorry, I'm hearing some audio. Is there someone asking? Okay, good. No. So I don't think so. Then we can proceed with the second bit of the talk today. So this is about the deployment. Okay, so we already had a good idea in these first two talks that this is all about flexible deployment to multi-cloud, and now we're going to dive deep a little bit in there, I suppose. And again, we have two speakers, Etienne Brosse from Softeam and Maciej Riedel from 7bulls.com. I suppose Etienne is the first, right? Right. So I will stop sharing my screen and you can go ahead. And once again, floor is yours. Thank you.
Thank you. So I'll try to share my screen. View. Just screen, the screen. Okay. Do you see my screen hopefully?
Yes. Yes.
Okay. So as has been already mentioned by Gerd at this first presentation, one starting point of all the morphemic and melodic methodology is what we call Camel models based on Camel language. Camel has been developed during the melodic project and it's been updated. Currently, we are and we are updating it with a goal of Camel 3 by the end of morphemic project. To be able to model such detailed such things, in morphemic project we developed Camel, what we call Camel Designer, so software in order to be able to model Camel model described by Camel model. Among these aspects, you do have different kind of the aspect, but I want to show you a bit of the three main aspect for Camel model. First of all is what we call deployment in terms of component. Gerd already mentioned that for an application or software is kind of component providing black box description, which is deployed and communicating to other component. The second important part of a Camel model is what we call requirement, where you can specify these different constraints you want to apply to your deployment and which should not be violated. And last but not least is what we call metric model, because in order to be able to evaluate or compute the constraint, sometimes you need to sensor to measure part of your model, part of the execution or different aspect of your deployment application, and then compute for each of these attributes you measure, compute some formula, and try to see if the result of this computation violate or not your requirement. So we got different examples which are already provided as open source in Camel 2.0 and Camel 2.5. This is a simple example where you got three components. At the center, you get an application which communicate with two databases through ports, and you have different configuration in order to be able to launch or download or start your application and your database. So that's what we call black box oriented. So you do not have any or few idea of what is inside the component, but the main idea is to describe your application in terms of Camel component and port or communication through this component. The second aspect is the constraint or the requirement described in Camel. The first one is what we call an optimization requirement. This kind of requirement allows you to set up what the solution will be better than another utility function, which give you some result, and you can rank your design, your solution according to the result of this utility function. You can also put some constraint. For example, you get what we call some image constraint. You can specify the OS you want to use. You can describe, for example, if you want a public cloud, you can also specify the location where you want to deploy your application. That could be important, like as Gerd say for RGPD. If you want to store your data in a specific location, for example, Europe or different country, in order to be able to be conformed to the RGPD, you can also describe the number of instances you want to deploy, with a minimum or a maximum number of instances. You can specify an exact number of instances, etc., etc. So we have different kind of requirement of constraint, let's say, which allow you to describe the context and the different aspects you want to use or optimize for your utility function. And then in order to be able to try if solution computation environment is valid or not constraint, or is better than other, according always for your utility function. You can specify constraint. For example, you can describe different what we call attribute, which allow you to measure specific aspects or price of your data provider, the location of your data, some cardinality, some utility, and you can put some constraint. One example here is to have response time not too high, which allow you to get a response in time for your application. Another kind of metrics or variable you can have is setting or getting where in the world your application is located in terms of latitude, in terms of longitude. So we can have an idea of the location where your application is deployed, and if it conforms again to the Euro location requirement, and which give you some hint about utility function and if it's fulfill your constraint or requirement for your application. So this kind of designer or this kind of UI have been developed of an existing open source tool, but it's used mainly to specify Camel model. And by everything good in your Camel model, you can then export your model in different flavor. Where you got you can have an XML file, XML, or Camel native file. You can speak where you can export file in the desktop, export. So it translates your model in some XML file. And if we go to the desktop, you get a file where you got your application, the deployment models. So you get your components, you get 3 components, you get your requirement, and you get all the information provided inside the model in terms of metric, in terms of requirement, and so on. And this is the kind of model which be used by MORPHEMIC or MELODIC web application in order to be able to optimize deployment or to compute the better deployment you can have. And that is part of the next presentation. If Marcus is here.
Yes, I'm here.
I will stop sharing.
Okay, thank you very much, Etienne. So that would be, I would then share my board. Please confirm if this is visible, if you can,
yes.
See everything. Okay, perfect. Thank you, Etienne, again. I'm Maciek from 7bulls.com. I'm Java developer there. And in this short presentation, I want to show you this MORPHEMIC from the user's point of view, and also how we can deploy the application that Etienne just prepared. And later, when it is already deployed, how MORPHEMIC handles it, manages it, and can improve it. So at the beginning, we have this Morphemic platform that is already installed. On the left, you can see the UI. I don't want to go too much into details about every bar you can see here, as few of them are platform related, as manage our settings. And also most of them would be more comprehensible when we go through the deployment. And I will explain majority of them later. The one I would want to say about now is just simulation. As we can launch, this is a nice feature of Morphemic, that we can launch the entire deployment in a simulation mode, and such simulation details would be available here. Okay, before going to deployment, we need to define our provider settings. Provider settings are pretty much our credentials to the cloud. So here I have already credentials of AWS and OpenStack, but as we today would go with OpenStack, you can see that I have already set my credentials here and a few important properties. Alternatively, one could use also bring your own node settings, but today we would go with AWS Cloud. Then we go to the deployment. And here we can see this is only about four steps, pretty straightforward here. We just need to upload the model that Etienne has prepared for us. It just takes from seconds to a minute, so it doesn't take long. At when it is able to start the application. Later, we just need to specify what cloud we are using. The last step, which is pretty much just pushing the big green button that would enable us that would launch the deployment process. As it takes a few minutes, I already started it about an hour ago. So we would be able to see already when the entire deployment is done. So I would then go to the view of the deployment, where we can see all the steps of we're exactly doing here. But to better understand that it is not just starting the machines, I would also show you the diagram of this FCR application, that maybe it would be more comprehensible to what exactly we are doing. And I believe few details needs to be explained here. That in this application called FCR, we would have three components like server app, load balancer, and database. And what users would be actually doing, they would be encrypting and decrypting files that are later saved to the database. So pretty much the server app is the component that is responsible for the computations, and that all of these components would be launched in this AWS cloud, and Morphemic would be taking care of the entire process. Going back to the deployment process, I would like to explain all steps as I think they're quite important. And the first one is those fetching offers, where we communicate this is the first time where we communicate with the cloud. And this is this downloading, this is this checking of what node candidates we have in the cloud. Later, generating constraint problem and reasoning. This was well described by Ger, but here in this, I have to show you how exactly it looks in this situation. And we have all the variables that were defined in the model. Here, for example, as all the constraints that we have for the hardware, what are the requirements for all of those components, or for example the cardinality of the app. The reasoning is the very important step. The moment makes the decision of what is the current configuration, fulfilling all those requirements from the model. But as it was mentioned, at this point, it would be the easy solution. So at the beginning, we would have only one server app, one load balancer, and one database. As for a best solution, we have here this utility function. In this deployment, in this simple app, we use a simple utility function, which is just optimizing the cost of the current configuration. As Morphemic, of course, has access to the prices of the nodes in the AWS. Later, during deploying, Morphemic starts the virtual machines, and also before launching the application itself, it also installs all the software that is necessary. So for example, Docker or Java, everything that is necessary for our application to be able to launch, to be working properly. When the entire process is finished, we have a living working application. So now I could switch to the Grafana tool, which is a monitoring system of our application, to which we can easily navigate from Morphemic. And as I started, you can see multiple diagrams here as I started the application about an hour ago. What is worth noting is at this moment is this red line, which indicates the values of response time metric. Going back to this diagram, you are able to see that Morphemic not only launched the application, but it also established a communication with those components. To be more specific, with those instance of this component, it gathers data. It gathers response time metric from each of the instance of this component, and later it merges it into average response time metric, which is visible here, and this is this red line. And what is extremely important now is that Morphemic just not only take care of the deployment, but you also improve it now. And based on this average response time metric, it can make a decision to reconfigure. So in this case, we have a threshold. So if this metric goes too high or too low, the reconfiguration process would be starting, resulting in better solution. So if we go back to this deployment process, we would be able to see reconfiguration process, which is slightly shorter than the normal deployment one. But you could see that those steps are pretty much similar to the ones that we had before. And this is understandable, but now we have more data, which is why this process looks different. And now in reasoning, we would have this average response time value, and this would give us the ability. This would give the ability to Morphemic to find a better solution, the more optimal one for the current situation. For after the reconfiguration, we would have more or less server apps components. So in this case, Morphemic can make the decision to increase cardinality of server app component, or decrease if necessary. The response time is too low. So the idea is quite simple. For example, the more users we have, the Morphemic would adapt to the situation, making sure that the application is working properly and giving results on time. So this is already quite a powerful tool, but recently we have added also an additional feature to Morphemic, which is forecasting module. And as you can see in the diagram below, where we have predictions from the forecasters. We have multiple forecasters like NBITS, TFT, CNN, or ARIMA, for example. They are predicting this average response time metric from the future. So pretty much what Morphemic is doing here, it can predict that, for example, there would be increased usage of the platform, and just before it is needed, Morphemic would make a decision to change the configuration. So it is an insight into the future. You can see here that this is the line. This is the line showing merged predictions. That this is indeed into the future, as we are before 3 p.m. And here we are predicting only a few minutes forward, but it could be easily tuned to have predictions for much longer periods. And of course, with longer time of running application, we would have much more accurate predictions. And the idea of reconfiguration now would be the same, that Morphemic would adapt and find a better solution predicting the future, which is, in my opinion, really powerful. And what is really worth noting, I think, is that you might have seen that I pretty much hasn't interfered at all. From the beginning, I just pushed the big current button. Then who was in charge. He totally deployed. He was totally responsible for the entire deployment. of installing the application and later for managing it. So I could leave it as it is now, and Morphemic would do the job entirely without my interference. Okay, this would be all for this section. Later in the next section, I would also like to show you for now, it would be all. Thank you.
Thank you very much. Once again, I'm asking if there are questions from the audience, or Verena, let me know if there is something in the chat while this section was going on.
Not at the moment, Giovanni. Let's go on.
Okay. So I think we can just flow through in the next third part, where after the architecture and conceptual model, and now the deployment and let's say the tools, now we're going to see a couple of concrete use cases. So the first one is about the big data Genome application, deployment and adaptation, and it's an interface with, as you can see, with the Spark. And then we have another use case about use case of Melodic, in this case for AI-driven investment platform. So Maciek first again, sorry, are you presenting immediately afterwards, or is it for Pavel?
No, I think I could start, and then.
Very good. Then go ahead. Once again, thank you.
Okay.
Stop share.
Yeah.
There you go.
Let me share again. Okay. Here at this moment, I would like to show you a different application, which is different. Entire deployment process again, but I think it is worth showing it that it is much more developed. And it is also interesting, as this is not just a testing scenario. This is a real-time, this is a real case scenario, which is called Genome. And this application was prepared with a collaboration with University of Białystok. And it consists of analyzing the big data sets of both genomic and genetic data, and based on the binary variable. As one of the methods, it uses also exhaustive search through the entire space of tuples. So you may imagine that with big data sets, it would be extremely time-consuming and resource-consuming, and quite power-consuming as well. But fortunately, this application is scalable, and it is just perfect for Morphemic to show what Morphemic can do with it and how we can then optimize it. The architecture is quite easy. It was mentioned already. It's quite simple. It was mentioned already that we are using Spark. So there will be only two components. I don't have a diagram for this, as there are only two. And the first one is Spark Master, which is a tool for distributed big data computations. And it gives us, it has multiple jobs to be performed. Those simulations about Genome already mentioned that needs to be done by workers. And we started with one worker, and then we start with one worker, and then we would have multiple of them that we need to make sure that they will do the job. In this case, we also have slightly different type of application, as we also have time constraint. Today, I put it into 1 hour. Only 54 left, but in a normal case, it would take days to perform all of the computations. And of course, there would be more simulations to perform, not only, as you can see, almost 600 of them at the beginning. But in this case, we started with almost 600 of them, and we have 1 hour to perform. And Morphemic would be looking if all the jobs would be performed on time, and if needed, it would increase or decrease the number of workers. I want to show you this metric model that we have here, or pretty much a diagram that helps us to understand what is going on here. And as you can see, this is more sophisticated than it was in FCR. We had only one metric there, but here we have multiple of them. We are also merging them to get more data. And MORPHEMIC is doing all this job. So based on this, based on those monitors, based on this data fetched from the workers, fetched from the system, it counts 2 constraint metrics, which is will finish too soon and not finish on time, which gives us pretty much an information if we are about to finish on time, and also minimum course. And this variable is not yet known. It will be counted by MORPHEMIC during the reconfiguration process. So those 2 metrics would give us impression if we need to reconfigure or not, and this minimum course would be the variable counted during the reconfiguration process by MORPHEMIC to determine what is the number of workers that is needed for us. Okay, based on this, the MORPHEMIC would start a reconfiguration. You can see all those diagrams here. There are quite many of them. But what is important here is that MORPHEMIC would perform the entire job here. I see that currently the reconfiguration process is taking place. So I expect that in a few seconds or maybe minutes, because the reconfiguration process takes around 2 to 3 minutes, we would see a big green light, and also the estimated time for the rest of the computation would go lower, and predicting that it would be on time. If, for example, there would be too many workers, the MORPHEMIC would choose, for example, to stop a few of the machines, to kill them, to make sure that we don't pay for unused workers, and to also optimize the cost in this situation. Okay, that would be all for this presentation. So thank you very much, and I think I can give voice to Pavel.
Or would you like to continue immediately?
Yes.
There you are. If you could stop your screen.
Okay.
Perfect.
Good. So again, good afternoon. My name is Paweł Skrzypek. I'm CEO of the AI Investments. My screen. One sec with the very right presentation. Okay. I hope you can see my screen.
Yes.
Yes, it's visible on screen. Thank you.
Good. Okay, as I said, I'm CEO of AI Investments, Polish company which aim to use the latest achievements of machine learning AI for the investments purposes. Yeah? We have created the fully automated investments platform, which allows, which is using machine learning elements, especially in the time series forecasting and optimization for the investing purposes. Yeah? The platform is fully automated. It follows the quantitative investing approach and systematic trading. And as machine learning AI based solution, it requires a lot of the computing power. Yeah? It operates currently on over 200 different markets, different financial instruments. It trains over 400 different machine learning models. For the training models, we are using machines with the GPUs. For the making predictions, we are using serverless components to save the cost of computation. We are using on 3,000 simultaneous instances of the Lambda services, 3,000 threads for the portfolio optimization, and the platform itself needs to handle over the up to 500 events per second. Yeah? So this number are shown to awareness, impression that our solution needs a lot of the computational power. So the optimization of the resources is a key thing for us. Yeah, I will show what are the results and of that optimization, but just to give you some overview, what is the scale of the computation. Yeah, and the AI investments platform is fully operated commercially. It is used currently by the Luxembourg-based investment fund Omphalos. So it is fully commercial application, which has been developed and now is used in production using Melodic. So Melodic is used for the deployment and for the dynamic management and scalability of the AI investments application. I will briefly show how the scenario looks like. But before that, I also wanted to say that currently AI investment is using typical hybrid multi-cloud architecture. So we are using two different cloud providers, and we also have our own on-premises infrastructure. So it is the, say, model case for like Melodic, and also the benefits are very concrete. About Melodic and the future extension MORPHEMIC, Geir told a lot, so probably the all features are clear. From our point of view, or to dynamically scale the application based on the needs, yeah, because the workload for the AI investment is very non-constant, yeah, because there are periods when we need to train more models to make more prediction, and of course there are periods when the platform is almost not used, when most of the markets is not working. What is a typical business goal in the AI investments? There are many business goals, or at least several business goals, but let's consider the most typical one. So the most typical business goal is to train given number, like 50 predictions models in a given time frame. For example, 1 hour. Yeah? We need to retrain 50 forecasting models, and we have the limited time to do that. And of course, we want to use as low number of resources as possible. And how it works. The investments analyst in AI investment is starting the training or retraining process. And in the first step, of course, the on-premises resources are used because they are already exist, they are already bought. So the marginal cost of using these resources is very low, almost zero. So it is natural choice to start with the on-premises resources. But of course, usually on-premises resources are not enough to finish the training in the given time frame. Yeah? And that is the moment that Melodic, based on the values of the generated metrics, is deciding to add new resources in the cloud. And all operations are done automatically. So new components, new training workers are that the infrastructure is provision of again, everything is done automatically. And even before that, of course, the most optimal resources are selected. So Melodic is selecting the cloud providers, selecting the type of the resources, so which virtual machines with the GPU to use, and this and deploy the worker application. The worker application is automatically connected to the central platform and start to process the training. Yeah? As you know, the machines with the GPUs, accelerated machines in the clouds, are very expensive. So the optimization of that process is very important. Yeah? I will show how much we can save through that optimization. But let's continue with our use case. The Melodic is calculating that total time to finish the processing is 3 hours. So the new machines are added, and the total time is calculated again, and again new machines are added, and more machines are added due to finish the training and processing in 1 hour. Yeah, when Melodic decides that the resources are enough to finish the process in 1 hour, then the process of training is continued. Finally, all of the models are stored using the cloud storage, and after the finishing training and of the cloud sources are removed, of course, checking if there are no waiting trainings or there are no jobs to process, and all of these resources are removed just to save the cost. So as you can see, the use case is quite simple and very similar to what Maciek presented. The application, but the results are, say, impressive. Yeah? Because thanks to we have analyzed in the AI investments many options for the infrastructure and deployment and training, starting from the fully cloud deployment and finishing on the fully on-premises deployment. But as you can see, the most optimal deployment is the hybrid one, with the using on-premises resources, but using cloud to handle the peaks of the workload. And as you can see, the difference between the on-premises only and cloud only variants and the most optimal hybrid one are huge, especially for the small and medium SMEs. Yeah, the savings can be really significant, and that is exactly the case for the AI investments. Thanks to lowering the cost of the processing data, AI investments is able to compete with the much bigger investments companies and quantity. Of course, it's not the only benefits. Yeah, the results, investments results achieved thanks to the AI investment platform are also very positive and competitive, but the cost can be keep very low, especially that we want to further develop our platform, to add new markets, to process more data, in that case, the multi-cloud and hybrid cloud optimization is the key element to gain the competitive advantage. Yeah, so the summary of the benefits. The first one is quite obvious, yeah. So it's effective optimization of the resource consumption. The second one is some kind of the sideways effect. So we have the scaling framework for the machine learning training. Thanks to this deployment, we have automatically scale the system based on the current workload. And the third point, that is very important from the business perspective, so we can optimize the work of the application relatively to the budget. Yeah, so we are sure that we will not exceed the budget, and within the given budget we can maximize the efficiency. So train as many models as possible or as fast as possible, and it is just a matter of the proper utility function construction. And again, the last some kind and somehow sideways effect is that hybrid deployment gives us the ability to have the high availability configuration, because in case of the failure of the on-premises infrastructure, the components are moved to the selected cloud providers. So in that case, application is still working, because we are using more expensive resources, but the business continuity is achieved. Yeah, the same in case of the failure or outage of one of the cloud provider. As we can see last time, the application which is not deployed in the multi-cloud, which is quite strange for Facebook, but that's the reason that having the multi-cloud deployment will also work in case of the outage of the one cloud provider, or in case of the misconfiguration of the routing protocols and so on, because you are always able to deploy to the different cloud provider and have everything up and running, thanks to the properly designed multi-cloud or hybrid cloud infrastructure. Okay, and yeah, I think that's all from my side. So thank you very much. I hope you find it valuable and inspirational. More information is available on the Melodic website. There are a very detailed description of the AI investments use case. Yeah. Thank you very much.
Thank you very much to you both. They were both very interesting and, yes, inspirational use cases that really help us understand also, you know, the practical, immediate, very measurable benefits, I would say, of flexible deployment and automatic management of a complex cloud system. So we close now last section, and sorry, I haven't asked if there are pending questions. Sorry, Verena. Otherwise, I can proceed.
There are no questions in the chat, Giovanni.
Okay, good. Then we will do maybe at the end. So the last section is again about the research situation, but this time, of course, we are looking forward, because this is, I suppose, about the challenges that are still open and where do we go from here. So I hand over again to Geir from University of Oslo. I stop sharing my screen, and then you can start again. Thank you very much.
Thank you. And I hope that you can see my screen now. Let's see if that reacts.
Yeah, now it's in full screen. Yeah.
Good. So, well, we have come quite a way in Morphemic, but there are still challenges to do. I mean, one thing is we have talked about forecasting, and basically the idea there is that we do the deployment at one time point, and then of course the measurements are coming in, and the measurements will, as we said in the beginning, tell us something about the application execution context. So for instance, with a genome application, it will for the computation, because the measurements there will be the event finished simulation. So these are the type of events we are talking about here. And the event management system will always compare this against the constraints of the model. And if there is a detection that now we can't make the constraints, or the constraints are violated. So for instance, at time 3, the system or the event reach these service level objectives, then it will call upon the meta solver in Melodic. And what happens then is that the configuration context freezes at time 3, because we use a mathematical optimization solver, and this solver will then call upon the utility generator with a proposed configuration for this actual context and for time 3. Then the utility generator will try to predict what will be the performance of this particular configuration, and then eventually send back to the solver the utility value for this proposed configuration given the context at time 3. Now, and this will iterate and iterate and iterate and iterate until the solver finally finds an optimal solution, which we mark here by a small asterisk, a star. And this would be the optimal solution for time 3. And then it will pass this back to the meta solver, which will then call the adapter. And the adapter will then call on the executionware to actually deploy this reconfigured application. So maybe by, say, time 28, we will have reconfigured the application based on this new optimal solution. Now, what we have actually configured at time 28 is the optimal configuration for time 3. Okay, so this is a whole motivation of the proactive aspects in Morphemic, where we try to predict the situation as it will be at time 28, so that instead of freezing the application configuration context, freeze it for our predicted time 28 and then solve the problem again. But it's worth mentioning that this is still reactive to what is supposed to be the situation at time 28. It is not taking into consideration all the events, the measurements events that are coming when we are doing a lag, and all the measurements in this situation is not taken into consideration by this solving. So what we are looking at is solvers that actually can work continuously and can continuously take into consideration these new measurements as they arrive, and are not depending on freezing the current execution context as we are doing now. Also, another issue is that this is composed of a solution time and an adaptation time, and both of these will of course depend on the problem itself. So if there is a difficult configuration to solve, then the solver will take a long time, or if there is big adaptations to be made, then the adapter and the executionware will spend a lot of time on that. So both of these times are sort of unpredictable, or at least random. And in the end, all of this will be making sure that how long into the future should we predict? That is a random variable. So eventually we should be able also to do this prediction with some kind of probabilistic guarantee that in 80% of the cases, we will be able to predict long enough into the future so that we are able to do both the solving and the readaptation by the time we have sort of predicted the context. So this is one of the core issues. And still, even though we can have this kind of continuous solver, we still have an issue, because there could be other missed service level objective violations on finding a new configuration and deploying this new configuration. And what should we do then? Should we stop? Should we start again? Should we? This is something which is not yet clear, and also the delay between or between service level violations is also not known, because it depends on, for instance, the arrival pattern of users, which is in general not known. So from will have challenges connected with just being predicting what is happening, and we are working to overcome them. We hope that we can get at least much longer than we are today by the end of MORPHEMIC. There will still definitely be open issues in this landscape. Another thing is that modern systems, they have are distributed, as I said in the beginning, on the cloud continuum, from the data centers of the cloud until the cyber physical world, where we actually do some of the operations. And there are different views on this. The classical view is about content and content caching, and this has been done for some time already. This is nothing new, but this is typically how we would distribute this kind of content across the cloud, fog, and the edge. And of course, this can be helped by storage virtualization. So by virtualizing the storage across all these different infrastructures, you can get a coherent view, and you can also better optimize where to place these different elements of the content. When you have content, you can also use the content for both AI training, which typically will require you to use cloud, as Paul just talked about. That training based on market data will typically be done in the cloud, because that is very compute intensive. Their models, then you can apply them in the fog or even in the edge in order to make quicker decisions. And as we said, AI training typically needs or requires high performance or high throughput computing, depending on whether it's simulation based or more high performance based calculations that must be done. So this is typically what has been done around this today, but in the end, we also have the physical world out there that needs to be done. Now, if you are lucky, then you can do also the event filtering in the physical world. However, in the physical world, many of the devices are battery driven, and I don't think you can do extensive calculations on battery driven devices, because then the battery runs out and you're lost. So in the end, you will probably move the event filtering to the edge. Because that is the closest place where you have capacities to do anything with respect to the physical world. But when you do this in the edge, then of course you also need to take into consideration where these events are coming from. And one typical example of application used in the physical world is automatic control loops. So for instance, if you are monitoring and controlling the temperature of a room, take a very simple automatic control loop, then the heater of that room will be controlled by a thermostat, which is the closed loop control on site. That will never be moved into the cloud. But the temperature readings of the room will still go back to the cloud for event filtering, in the sense that you will detect when you are outside of the comfort temperature in that room. And in that case, you will do some kind of complex event correlation. So maybe you can detect that if someone is watching Netflix at the same time, then the temperature goes up in the room, or if they go out of the room, then the temperature goes down and you need more heating. Complex event processing. Event filtering can also be used to set new set points for the temperature. So instead of saying that, okay, now there are nobody in the room, so we have the set point of 15 degrees. Now there are people in the room, we increase the set point to 21 degrees, which is more comfort temperature, 22 degrees, which is more of a comfort temperature. And then finally, you could also have high level optimization of the control system. So for instance, again, going you could decide at a high level to, for instance, switch off heating when there is a longer period of absence. You could do the heating based on price signals from the electricity grid, for instance. But these are sort of high level optimizations, and you have enough time to do that, and you'll probably do that in the fog, or most likely in the data centers of the cloud. So from this, you see that there are different applications that will be split around different parts of the continuum. And I think it's very unwise. I've seen some examples where people have tried to move closed loop control into the edge. That is possible on the factory floor, but I don't think that is a predominant use of the edge computing in this case. So for me, this is sort of the mapping of applications across this continuum. Then, of course, we need to take into consideration the communication part of this. On one end, we have the radio frequency link, and the radio frequency band is special in the sense that it has bandwidth constraints. So we pump as much data as we want across this radio frequency link because that is physically constrained, and that is something we can't do anything about. We can't make water run upwards, and we can't increase the bandwidth of this infinitely. Although the engineers, radio communication engineers, have been very, very clever, constantly increasing the bandwidth that we're able to get across the radio frequency link. There are hard physical limits that cannot be achieved. You can approach this limit, but we cannot go beyond it. And also the radio link is a shared medium. So you need to access all the devices shared way or the other, and you have to give them access to this shared medium according to some kind of advanced policies. And this is a challenge, of course, restricting the capacity of the radio frequency link. On the other hand, my claim is that on the backend side, from data centers to the radio access network, you typically have fibers. And fibers, they do not have any bandwidth constraints. You can pump fibers. And also you can have network virtualization so that you can make sure that your data is flowing according to needs, so that if you have a real-time stream, then you can make it faster through this pipe than if you have, say, somebody streaming Netflix or a film or whatever. Okay, so on the radio side, you also have something called software-defined radio, which is, again, software which can be parameterized and also can, in the future at least, be used to maybe give better access to some applications on this shared medium. And if you are able to coordinate these different virtualizations and this kind of software storage, software network virtualization, and software-defined radio, we actually do have quite an interesting optimization problem to solve. But we have to look at the round trip time budget. So as I said earlier, there are three things about computing which are taken for sure. You have to get data in, you have to compute and do something with the data, and you have to send some results back, okay, to somebody. Now, this means that for the data transmission, you need to consider the size of the data, which is quite obvious. But as I said, on the fixed fiber, there are no bandwidth restrictions to data. But of course, you need to take into consideration the time it takes to send data. The more data you send, the longer it takes. Also, the protocol used to send the data will have a strong influence on the time it takes to send the data. The link speed will, of course, matter, but not as much as the former two. And then, of course, the route of forwarding will decide how these data is sent. If you send data constantly around the world in order to, of course, that is not very efficient and will create a longer delay than if you could send it directly across the wall. And then, of course, when you have the data, you need to consider the computation time, which is, in general, data dependent. So if I'm asking to do a complex calculation, say, on an image, that is, of course, much more time than if I just want to open a file, say. So all of this needs to take into consideration. Also, computations are normally multi-component. So think parallel computing, where you have many different components talking together at the same time. And then you also have to take into consideration the execution platform. If I execute something on my mobile phone, that is in general much slower than if I execute it on my portable computer, which is again much slower than if I execute it on a powerful server in a data center. So eventually we also have Amdahl's law, which tells us that there is a limit to how much we can achieve of speed up even if you go parallel. So this example, if you look at the green line here, this is an application where 95% of the application can be made parallel. And even if you assume that it is perfectly parallel, then the more resources you throw at it, you get a limit of about 20 times the speed of the CPU, which means that the limit to the scalability. So pumping more CPUs might not be a solution to your problem. So you need to take into consideration the parallelism and how you exploit your cores in your application, but also when you deploy the application. So for instance, an application that scales well like this one with 95% parallelism will probably be better off being deployed in the cloud, whereas an application round trip budget will probably better be installed or can be installed on a single core CPU because you don't use more than that core anyway, right? So we have certain problems in the future for this multi-objective placement optimization that we are targeting in melodic and morphemic, and one is to satisfy the application requirements from the application components. This has already been done in melodic, and we are just extending it in morphemic. So this can be considered more or less done, but not in a context of a cloud continuum. Then the data location, and for the data location, we have to look at what is going to be sent upstream and what is the data location downstream of the calculations. So where do the data come from and where will the data be consumed after being calculated? This allows us to calculate the round trip budget for each calculations that we are doing. But to bear in mind that these are data dependent, so the same component can need different times depending on what data it processes. In other words, this is a stochastic distribution. This is a statistic decision that we are going to make in this case. And then, of course, different parts of the cloud continuum can charge differently for using calculation cost or storage or even network. So you have to take that into consideration when you decide on the distribution. And finally, in the future, we will have software defined everything. And what can we do about that? I mean, in their own APIs, there will be many different operators along this line. What kind of guarantees can each operator give you? What kind of contract commercial assignments do you need in order to use their APIs? How freely can you use their APIs? And what if many people use the same APIs and many people require like low latency from the operators at the same time? In 5G, you have the concept of slices, which are supposed to solve this, but seen from the operator. So the operator can solve it with slices, but how do the operators serve requests coming from third-party application users using their infrastructure? This is something which needs to be investigated and needs to be solved, I think, for the future. So thank you. And now I think it's time for questions.
Yes, thank you very much. It was very stimulating also as a wrap-up, and I think, yes, it's inspiring questions. Do we have anything from the audience, Verena?
In the chat, I don't see anything, but if you have questions. Okay,
if someone has something, they please can either write on the chat or let us know. I have a few questions. And I mean, I could go backwards also for the sections, but I would like to start first with this one. And I wanted to ask about the case of this multi-objective optimization. No? Do you see also an aspect for green computing and sustainability to be dealt with in the future? That seems, of course, an important topic. Do you think we have already the data to do this, or what are the constraints that we need to have from the grid, for example, to be able to do that as well?
Well, the grid, the data we need from the grid is basically the energy. The energy is produced from renewables. When the wind is blowing, there is a lot of energy from windmills. When the sun is shining, there is a lot of energy from solar panels. So we need to know the greenness of the grid. Now we have been through a period where there has been actually little wind, which has made, at least in Germany, to be found by gas, which has also driven the gas prices up in Europe, right? So we need this continuous information about the energy mix from the grid, because that allows us to optimize the placement and the execution of software. Now, it should also be mentioned that the energy efficiency of data centers has been exponential over the years. So that means that the energy per megaflop, if you want to use that as a measure, is almost constant. And it has been almost constant for as long as we have had data centers in scale, at least for the top 500 data centers. So that means if you really want to do something which is green computing, then you should really strive to push the calculations towards the data centers and not towards the cloud, because in the cloud, in general, the CPUs are much less energy efficient than they are in.
You mean the edge? You mean the edge?
Yes.
Yeah.
So this is also you can take that into one of the objectives of your optimization problem to decide where do we put the data in green energy to the largest possible extent. But of course, if the edge computer is based and driven by solar panels, then again the question becomes then they are free, then they're green, always green, independent of what the grid is providing of electricity. And in the same time, we also have now the declarations from the big data center and cloud providers saying that into the future, most of them will be driven by renewable energy. So again, this benefit, which now can be awarded to the edge computers by having local installations of solar panels, will disappear in quite a few years when also the data centers will be powered by renewable energy. So it's a fluctuating market. It's easy to make it. Here.
Yeah, I always heard of carbon-aware routing, so even the networking transmission cost could also be balanced. So, but this is the direction that you see, right? That to have this multi-objective optimization, also with very diverse, let's say, elements of the utility vector and this kind of thing. And I have another question on this new perspective talk before moving back to the others. I'm happy that you mentioned the control loop, because on the previous slide, now when you were saying about, at time T3, we freeze and we start to think, but the world goes on, and then at time 28, this is a classic problem, even with linear control. Not if you have a delay, it's already risky, and if you have a non-linear thing, it's even worse. So I wanted to ask, is there some, what is the state of research on applying stability or system identification kind of things, or the control, engineering control stuff to this problem?
This is what we are working on now, because we realized this problem, and exactly as you said, there is a system stability issue here. So if we could use this kind of continuous linearization methods that are used in automatic control, and sort of build a pure input-output model, where we do this for every event, we do a new linearization, we update our view of the model in the next phase. If you can do this continuously, then this is what we hope will be able to overcome this delay we see now.
Okay, thank you. Again, take a step back if there are other questions from audience. Otherwise, I can go on with things that are also about the previous presentation. So then everyone from the speakers is welcome to join in. I don't want to Okay, so then maybe I have one on the tools. So this, I don't know if it is for Etienne, but he was presenting them. But I saw that you are using a UML tool, right, tool as a basis. So you have this kind of diagrams. And I wanted to ask, I mean, I've seen that, if I remember correctly, in the diagram of the requirements, let's say that there were a lot of boxes, but not many arrows, right? So there was a little bit disconnected. Maybe it is an example. My question is, do you support composability of these things? Like if I want a metric, it's a derivation of the other two, like the greater of the networking time and computation time must be lower than a certain limit. So do you see these kind of things like having libraries of part of the models that could be reused? Is this how you see the of this application modeling?
Yeah, there's two aspects. First of all is the language definition, which allow the reusability of such metrics, and it has been implemented inside on top of our UML models. So you have this reusability. You didn't see links because I show you some diagram where you had just a view in order to show you the different elements and so on. But you're right, there is links between them, and you can reuse or set different links in order to be able to reuse part of the model. So it has been not hidden, but I just wanted to show you different kind of requirement.
Yeah, I agree. This was very good for the overview, but I was curious about that detail. Okay.
Beyond, you have some graph or you have links between them or metrics. And so Camel also allow reusability, and there are also some aspect regarding to the tool, where tool allow you to provide and define library, which can be reused in different model, but of course library related to the tool, not really library related to the models. The fact is, Camel language come with a predefined library in terms of type, in terms of template, metrics, and so on. And you can start from this library. And the same way, you can start with this library inside the tool.
Is Camel a formal language with a grammar? So theoretically, one could write a source, or it is this is hidden by the tool, and you only have the XMI representation?
No. With grammar, with an OMF Nico grammar, but of course it's hidden inside the tool. So you get different files. The tool implementation is also open source, is available, and the language itself in terms of OMF eco modeling is also available, but of course it's hidden on the tool.
Okay. Thanks. Then maybe I have another question. I don't know more about the crawler or about the tools, but I wanted to understand what exactly you do with the source code that you download, because I understand downloading the source code, and it can also maybe compile it on the fly with some pipeline of continuous integration. But if I got it right, you want to extract the typical performance profiles of something, right? So there is this famous database that has problems when it runs on more than 8 nodes, it gets slow. And so you know that, right? That's what you want to do. So how do you do it from the source code?
Okay, not only the source code, like the structure of source code, as for example, the comment, the conditional, but also important application to define the correct profile in order to provide the best deploy model based on the script or other type of the deploy model. So it's very important for the profile, the application profile, to retrieve see the application based on other type of information, and this is downloaded from this source repository in this moment. For example, GitHub provided the information as a topics label, and based on this is searching the best deployed model.
Okay.
This is not only source code. Source code is one of the entry point for the crawler. Okay,
yeah.
For the information project provided by the project, but we have other type of information.
Okay, thank you. Now I think it's clear too. Thanks everyone. Indeed, these were the questions that popped into my head while I was listening to your talks. I don't know, Verena, if we have other questions or we have some minutes left.
Not in the chat. If someone else wants to raise a question, please feel free. Otherwise, Giovanni, I think you can close.
Then thanks once again to all the speakers for the very, let's say, diverse, but I think working together very well, the kind of angle, influential deployment to commercial use cases with hard benefits that you can really plan for and measure at the end, and also a perspective on the next steps. I also thank everyone that attended, and please get in touch with us. I think in channels for our website and social media channels that you can follow for the Horizon Cloud program, and also for the now MORPHEMIC project that you can contact directly or through the Horizon Cloud coordination group. So
thank you very much.
Again.
Thank you.
Thank you, everybody.
Everyone.
Bye.
Bye. Thank you.